So now that we've set up some instance geometry for the debris, let's set up the sourcing and simulation for this. So I'm going to start by object merging in the static render geometry from the destruction section. So we'll point an object merge to object slash destruction slash render geometry. And if you display that, you can see this is not time dependent. It doesn't have the little clock icon, and it's just the static geometry before it's simulated. And there are various ways that you can set up your debris sourcing. So I tend to like doing some fairly custom debris sourcing, where I like to do something where I have a lot of manual control over exactly what's happening. There are some more procedural tools that you can use. For example, there's the RBD Connected Faces SOP, which can be used in conjunction with the RBD Disconnected Faces SOP, and this can be quite useful for finding out when faces come apart from each other. And we're on Houdini 18.5 here. Houdini 19 has some more debris sourcing stuff, but even though we have lots of debris sourcing tools, for example, we still have this debris source SOP also that essentially uses a simulation to determine when the debris should be sourced. All of these other tools are quite cool, but I still often lean toward manual sourcing setups, and for the purposes of learning some of these problem solving techniques, I think it's helpful for you to learn how to do some manual sourcing. So we're going to do that for this one. Feel free to explore the other sourcing techniques if you'd like, but this particular technique is one that I use all the time. So we don't necessarily want to emit debris from all of the super tiny pieces that make up this fractured geometry. Generally, I just want to emit debris from the larger pieces here. So let's start by adding a split SOP to split apart the small pieces. So I'll drop in that split, put it under our object merge, and the group I'll set to area is less than 1. So you can see this isolates all of the small pieces here, and in the second output of that split, we just get the bigger ones that we actually want to emit some debris from. These small pieces here are actually practically debris sized already, at least some of these smaller ones are, so we don't need to emit more debris from the tiny pieces. It's really the larger ones that need that extra emission. So let's drop a null on the second output of that split. Call this split tiny pieces. And now we just have the larger ones left over. And we don't want to emit debris from these outside faces here. We only want to emit debris from the inside faces that are essentially starting out underground. So we can use the inside attribute to isolate just those areas. And in order to access the inside attribute, we need to unpack this geometry. So drop in that unpack. Now we have the inside attribute available. Drop in a blast SOP, and we'll blast inside equals 0. So that eliminates our exterior faces here and just leaves behind the faces that we actually want to emit some debris from. Now there's a pretty cool trick that I like to use to animate my debris source points, and to do this we're going to just scatter some points onto all of these faces. So let's drop in a scatter SOP, and we're going to need to use a fair amount of density here. For something like this, I don't like using the total count option, so let's turn that off. And this is already much higher resolution, but we're going to need to go even higher res than this. I'm going to turn this up quite a bit and set a density scale of 30. And that took a moment to cook because it's creating a fair number of points here. This is over 400,000 points. But this still shouldn't be too terribly heavy to work with, and now that we have all of these points, we can actually apply the simulation animation to all of these debris points. And of course, this is such a dense point cloud, it's a bit hard to see. Let's perhaps turn our point size down to see that a little bit better. And whenever we scatter points on the geometry, we can pick up attributes from the geometry it's scattered on. So we can inherit the name attribute from the geometry that the point lies on. And currently, we don't have that name attribute getting picked up by these points. If you look at the scatter SOP under the output attributes, by default it picks up all of the point attributes from the geometry, and it picks up the normals and UVs, but it doesn't pick up any of the detail attributes or the primitive attributes. So under prim attributes, let's select name. And now if you middle mouse on the scatter, you can see all of these points have picked up the name attribute of the piece that they've been scattered on. So now we can apply the simulation to these points with the transform pieces SOP. So let's drop that in, connect the scatter to the first input, and for the second input we're going to need to object merge in the transformation points. So this new object merge, I'll point to object destruction and point this to the simulation transform points null that we set up over there. Make sure that this null is after the cache, or you're going to force the cooking of your RBD sim here. So let's jump over to that original RBD simulation. You can see that this null here is after the cache, so that'll make sure that we're not re-cooking our original RBD sim while sourcing our debris. So now that we have these transform points set up here, that's actually giving us nothing on frame 1. So let's scroll ahead to some frames where we actually have some simulation motion. Okay, on these frames you can see our transform points in action, and if you display the transform pieces, then this is applying those transformations to all of the scattered points according to the pieces that they were scattered onto. So all of these debris source points here are matching what the actual original RBD sim is doing. So this is pretty cool, and this is a trick that I use to do some other interesting things with destruction as well. For example, when I want to stick rebar pieces onto fractured chunks after the RBD sim, or maybe I want little bits of fragments of glass to be stuck to my RBDs, I will often scatter those extra detailed geometries onto the RBD pieces and then use this transform pieces SOP with those transform points to get the extra bits of detailed geometry like glass shards and rebar and such to stick onto the original RBD pieces after the sim. So that's just one extra little tip that you can consider when doing some more detailed destruction work. Anything that you can do to add detail post-simulation can be very beneficial. But to get back to the matter at hand, our debris sourcing here, we can use the velocity information to determine when we want to emit debris pieces. So the transform pieces SOP is adding this velocity information to all the points that it's transforming, but I like to generate a speed attribute from this, so let's drop in a wrangle. And this is something that you might want to consider adding a preset for. So I have one set up already. If you look at the gear icon here, I'm going to scroll down to the speed from velocity, and you will not have this by default if you haven't set it up yet. If I select that, I'm setting this float attribute speed equal to the length of the velocity vector, and you can set up your own presets for this sort of thing, because this is one bit of vex that you use very often. Not hard to type this out, but for these commonly used things, it's helpful to have these presets. So once you have that set up in your wrangle, just go to the gear icon and hit save preset and name it whatever you want, and that can speed up your workflow a bit. So I'm going to rename this wrangle to speed, and then we're going to drop in a blast SOP to delete the slow moving pieces. So on this blast SOP, I'll say at speed is less than 0.5, and the group type will be points. So if we display that, you can see this is deleting out all of the static pieces that weren't moving at all, or weren't moving very much, I should say. So now we just have the more quickly moving pieces, which are the ones that we want to emit the debris from. And also you can see that we have a lot of emission that will be happening underneath the ground here, and that isn't necessarily a problem, but because destruction work can be quite heavy, I really want all of the emission of the debris to happen above the ground wherever possible, because that's really where we're going to see it. If we emit a whole bunch of debris below the ground, then that's just adding tons of extra pieces to our simulation and to our caches that we're just never going to see. So to group all of the stuff that's below the ground, we can use our original geometry for the environment. So I'll drop in a new object merge, and I'll point this to object, environment, and out env low res. You can use the high res version, of course, but I think for our purposes, the low res one will work just fine. And this is going to be at the world scale, not the simulation scale, so that's going to need to be scaled down to match the space that we're working in here. I don't know if we have a simulation scale set up in this debris section yet. It looks like we don't, so I'll just pin my viewport in there, go back to the destruction section, and let's grab a sim scale from in here. It looks like we have a sim scale on our creature collider, so I'll just copy that, go back to our debris setup, and paste in this sim scale SOP there. So after transforming this down to sim scale, we can use this to group the sections that are below the ground here, and we might want to give this a little buffer as well, because right now, as soon as anything touches the ground or below, it won't emit at all, and we might want to give ourselves just a little bit of buffer space there. So I'm just going to add an additional transform here, and let's template display that, and move this down just a little bit in Y. I'll just try moving it down 1 unit, just so that it's not immediately deleting everything right below the surface. So now we can group all of our debris source points with that environment geometry. So drop in that group, connect our speed blast to the first input, that environment geometry to the second, and let's give this group a name. I'll call this below ground. The group type will be points, turn off the base group, turn on bounding regions, and the bounding type will be the bounding object. So you can see this is now grouping everything that's below the ground there, and we can just blast all of that stuff away. So drop in that blast, select this below ground group here, and we don't really need that below ground group anymore. So on the blast stop, you can just turn on this delete unused groups option. So we've done a good job so far at limiting where our debris sourcing will happen, but right now this debris sourcing, as it is, will just continuously happen for the entire frame range once things start moving. So we want this to start out with a fair amount of debris sourcing at the very beginning of this destruction and to kind of fade off so it's not constantly emitting. So there, as usual, are various ways that you could do this, and a technique that I like to use is to use an attribute wrangle, and we're just going to set a percentage of pieces to be deleted in here. So I'll call this wrangle kill percentage, and then in this kill percentage wrangle, we'll type in if the random number with the point number as a seed is less than some kill percentage, and we can define that with a parameter that we're going to add to our wrangle SOP here. So I'll type CHF, and I'll call this kill percentage. Make sure that you don't put any spaces in here. This string needs to be all proper characters. You can put in underscores like that, but no spaces. and then close that if statement. And if this is true, then we will do a remove point and then pass in 0 for the geometry handle, which is just the current geometry stream in the first input there, and pass in the point number that needs to be removed. And right now, because this kill percentage parameter doesn't exist, it's just going to default to 0. So this random number is always going to be between 0 and 1. So this is not going to actually kill anything yet because that's never less than 0. And now to define the actual kill percentage that we want to use, you can create this parameter automatically by hitting this little button here. And this will search for any of these channel parameter references defined by these functions like CHF, and it will create those corresponding parameters in the UI here. So after clicking that button, you can see that adds in this kill percentage parameter down here. And now we can just start by entering in some manual values. So if you put in 0.5, this deletes 50% of our points here. You type in 0.9, that's getting rid of 90% of our points, and so on. So we want this percentage to change over time. We want lots of emission at the beginning, and then we're going to fade that off. And before we set our kill percentage here, let's just check to see what our simulation looks like, to see when we want that emission to start and end. So of course it starts at the very beginning, but I want it to maintain its full debris emission for several frames. So let's say maybe up through frame 27 here, we'll keep full debris emission. And then by the time we get to perhaps frame 50, we should stop emitting our debris entirely. Now to apply that fade off over that range in our kill percentage parameter here, let's use a fit function and we'll remap the current frame number from 27 to 50. And at frame 27, we'll say we want 0% of the points removed. And at frame 50, we want 100% of the points removed, which will be represented by a value of 1. However, I did find that this was actually creating much more debris than I wanted and that my computer could handle. So we really did go quite overboard with the number of points here. So in the kill percentage, instead of deleting 0% at the very start of the sim, I actually wound up deleting most of these points because these are being added on every frame. So this is really going to add a ridiculous amount of debris every single frame if we're not deleting anything to start. So I actually found that a value of 0.98 worked pretty well for those initial frames. And part of the reason that I'm applying all this point removal down here is because, it really helps us to see what's happening, to have all of those points visible prior to this. If we had a very sparse point cloud at this point, then we wouldn't necessarily be able to get a good read on what our setup is doing before this kill percentage happens. And also, I want all of these points to kind of randomly choose which ones are being deleted at any given time. So if we were to use fewer points here, then we wouldn't be able to really have enough points to randomize which ones are being deleted. And right now, because we're just doing our random number generation based on the point number, and the point number is currently not changing at all in time. So if if right now we have a good 98% of our points being killed, actually closer to 99%. I don't know how obvious this will be in the viewport, but as we step through here, it's going to be the same exact set of points that are always being deleted. And I really want this emission to be a bit more random than that, so instead of just emitting from the same few points all the time, we can apply a sort to randomize the point order before this kill percentage happens. So on the sort here, drop that just before kill percentage. Under point sort, we'll set this to random. And you can see that this changed which points are being deleted here. And we want this to change on every frame, so we'll set the seed to the frame number. So on every frame, it's reordering all of the points, and thus it's changing which points are getting cleaned up by that kill percentage. So it doesn't look like we have very many points, and perhaps it seems a little bit silly to source so many when we're really not using that many for our emission, but we're actually using a much greater variety of points than it actually looks like, because due to this sort, this is giving us lots of potential random points for it to randomly choose from for the ultimate sourcing after our percentage has been isolated here. So now that we have our debris source points all defined here, we can go ahead and set up the actual instancing of these points. And I'm also going to change some of the attributes on them. For example, right now our velocity is perfectly matching the velocity of the pieces that they were scattered onto, and I generally like to break up these velocities a bit so that it's a little bit more imperfect and it adds a little bit more, realistic chaos to the scene. So I do want the debris pieces to pick up the approximate velocity of the piece that they were scattered onto, but we want to randomize that a little bit. So let's drop in this attribute randomize SOP, and we'll set this to uniform continuous. And for the min and max value, I'll say that I want this to pick up at least, we'll say 80% of the original piece's velocity, a maximum of perhaps 1.2 times that, so potentially an extra 20%, so these debris pieces can kind of get flung around a little bit. And I'll copy the first parameter and paste that into the Y and Z as well, so that the X, Y, and Z directions all get the same amount of randomization. So paste those references in like so. And right now the attribute randomize is defaulting to setting the color attribute, which is not what we want. We want to apply this to the velocity. And we don't want to set a completely new value for the velocity. I want to set a multiplier on the velocity. So if you bypass the attribute randomize, we actually have to look pretty closely at the velocities to see what it's really doing. And it's not a massive difference here. You can see that it's just varying up those velocities a little bit, so it's not perfectly picking up the directions from the original pieces. So I'll rename this to V variance, and then we can move on to actually instancing the geometry onto here, and we're going to do that with the copy to points. So these points will go in the second input, and the instance geometry will go into the first input. So let's line these up a little bit better, and then connect the debris instances to the first input here. That's the geometry to copy. And then on the copy to points, we can turn on this piece attribute, which will default to an attribute called variant. So we have to set up this variant on both the points and the instances in order for it to correctly assign instance geometries to the points based on that attribute. If you don't set this up properly, then it's just going to apply all of these debris instance pieces onto every point. So we have 11 different instance pieces here. So each point is getting all 11 instances applied. And that's definitely not what we want. You can see there's this warning here about this variant attribute not existing. So let's go ahead and add that. Under the debris instances here, I'm going to add it with an enumerate SOP. So I'll drop this after the file merge, and on the enumerate, I'll set the attribute to variant. And then on our points here, we're going to set the variant attribute with something else. So we can't use the enumerate SOP because we need to get values that just go from 0 to 11 to match the number of debris pieces here. So I'm going to use the attribute adjust integer option, and you'll actually see that this attribute adjust integer defaults to the variant attribute, because this is one of the more common use cases of the adjust integer SOP here, so that's a convenient default to set. The attribute class of point is correct. We can adjust this with random. For the max value, we can check the number of debris instance points here and subtract 1 from it. So I'll do another endpoints lookup, point that to / debris instances minus 1. And that's currently giving us a value of 0 because I made a typo. That should be endpoints, not endpoint. So after fixing that, you can see we're getting values from 0 through 10. And we can check that in our spreadsheet as well. If you pull up that spreadsheet, scroll over to the variant attribute and sort based on that, you can see sure enough we have values going 0 through 10. And now if we look at our copy to points, that warning about the missing variant attribute is gone, and we now have a unique piece being instanced onto each of those points. So let's also add some random rotation to all of the instances. For this, I usually use the attribute randomize, which will default to randomizing color. That's not what we want. Let's change the attribute name on that to N for the normal, and the distribution will set to direction or orientation. And finally, let's set the p-scale on the points as well to control the size of all these pieces. So for the p-scale, I like using the randomize SOP for that. So drop in that attribute randomize, set the attribute name to p-scale. And for this one, I like to use the custom ramp option. Now let's set our minimum and maximum values. So I'll say fit value 1 to 0.5, that'll be our new maximum, and value 0 will be 0.15. And right now this is giving us a linear distribution from the small pieces of 0.15 size up through the large pieces of 0.5. And this is one of those things that's very important to get right when you're doing effects work. That's the mix of large and small pieces. So generally speaking, you want lots of little pieces, a few mid-sized pieces, and very few large ones. So this is why I like using the custom ramp option here. So we can take this middle point on this custom ramp and drag that down and to the right so that most of this distribution is made of these very small pieces here. And of course you can fiddle around with this ramp to get exactly the distribution that you want. You don't have to be too terribly picky as long as most of this distribution is consisting of these smaller pieces. And it looks like we have some display glitches happening in our viewport here. Some of these pieces are displaying incorrectly. And this is probably not indicative of a real problem with this geometry. It's probably just a display issue. And sometimes we can get these little display problems to go away if we perhaps flip to the render view and back to the scene view. Yep, sure enough, you can see now that has fixed some of those display issues with those packed pieces. So don't be too alarmed if your packed geometry doesn't display quite right, because sometimes it's actually fine, even if it looks wrong. And now after setting up all of this sourcing, now we're in good shape to go ahead and start setting up the actual simulation.